I want to go over some sig fig rules. This isn't a comprehensive list of rules. It's just some basic rules to get you through the majority of the problems. So the first rule is regarding what I like to call sandwich zeros. So for instance, in the example, there's a 43 on the left and an 8 on the right. And since that 0 is sandwiched between two non-zero values, it is significant. So this value here, we're going to count all the digits as significant. In a similar manner, we have sandwich zeros in this value as well. And it doesn't matter how many there are. You could have 12 zeros in the middle of your sandwich and they'll still all be significant as long as you have two non-zero pieces of bread. So we got 4 sig figs with both of these examples. Our next rule is regarding placeholder zeros. So those are not significant. All they do is make our number really, really big or really, really small. So for example, 470,000, well, that's just a really big number and those zeros are just making that number what it is. The only two values that we're going to count towards our sig figs will be the 4 and the 7. We have 2 sig figs with that value. A similar thing happens when you have placeholder zeros with really small numbers. So the 2 zeros out front here, they just make the number smaller, and just the 6 and the 8 are significant. This is my favorite rule or favorite guideline, this third one. 2 things have to be true in order for a 0 to be significant. It has to be to the right of the decimal point. So first thing, is it to the right of the decimal point? Second thing we want to check. Number 2, is it to the right of a non-zero digit? If both of those things hold true, then it's going to be significant. So looking at the example, the zeros out front, they're not to the right of a non-zero digit. So they're not significant. 5 and 7, well, you don't have to worry about numbers that aren't 0. Now look at these zeros at the end here. What function do they serve? Well, they're to the right of the decimal point and they're to the right of a non-zero digit. That means that they're significant. So the end of this, 5700, all those values are significant, and we can say that this value has 4 sig figs. We can also classify those zeros at the end as trailing zeros, but the rules still apply. Are these zeros to the right of the decimal point? Well, yes. And are they to the right of a non-zero digit? Yeah, well, they're to the right of the 4. So because it holds true for both of those statements, we're going to say everything in here is significant, and the 4.00 has 3 sig figs. This last part is really important in lab, especially when you're doing an in-person lab and you have a limited amount of time. And they might say, well, add this sample, it might be in a test tube or something, add this sample and boil it in 400 mils of water. And I oftentimes see students measuring out exactly 400 milliliters of water. But if you're just trying to boil something, does it really matter how much water you use? Well, no. So this is just an approximation, right? They're saying use about 400 mils of water. Maybe use 450, maybe use 300. Probably doesn't make a huge difference. So the way this value is written, we're going to say that it has 1 sig fig. And you'll see that a lot of times with estimated values. You have these zeros that are just making the number a little bit bigger, and it's just an estimate. If it was really important that you add the sample to exactly 400 milliliters of water, then there's 2 things you can do. You could do 400 milliliters, and that's going to give you 3 sig figs. So putting a period at the end of your number tells you that those zeros, even though they look like placeholder zeros, that they're significant. For me, my go-to would be scientific notation. So I would report this as 4.00 times 10 to the 2 mils if I wanted the experimenter to know that they need to use exactly 400 mils. And why is that? Well, in scientific notation, any value, it doesn't matter, any digit, it doesn't matter if it's a 0 or a non-zero digit, they're all significant. Let's practice counting sig figs a little bit before we jump into any calculations. So on letter A, we have a whole bunch of placeholder or leading zeros. They don't count. So nothing, nothing, nothing. And then we get to this part, which is all non-zero digits, and those are going to be significant. So we have 3 sig figs for letter A. On letter B, another example of placeholder zeros, except this time those zeros just make the number larger. So I'm only going to count these first 3 non-zero values up front, and I'm going to say that I have 3 sig figs for letter B. For letter C, it's in scientific notation. I love scientific notation. It avoids ambiguity with the sig figs. Because it's in scientific notation, we know that all the values are significant. So it doesn't matter if they're zeros or non-zeros. We have 3 sig figs here. And then in this last one, we have all non-zero digits. So we don't have to think about it too much because zeros are where it gets tricky, right? So this is just going to be 5 sig figs. In letter E, we have a slightly confusing situation. We don't know if someone was being super careful and took their time and measured something and it was exactly 2,000 centimeters, or if they were just estimating and they're like, it's 2,000 centimeters. Who knows? We have to assume the worst. So we're going to assume that these zeros are non-significant and only the 2 counts. So I would report this as having 1 sig fig. Sig figs are not fun. One of the sets of questions that you might ask yourself to get through it is the 0 to the right of a decimal point? And is the 0 to the right of a non-zero digit? If you can answer yes to both of these questions, then the 0 is significant. If you get any no's on these questions, then the 0 doesn't count towards the sig figs. Let's use those same questions to help us with our analysis in letter F. We have 0.0800. First question, is this 0 to the right of the decimal point? And the answer is no, so it's not going to count towards the sig figs. Now I'm looking at this 0. This time it is to the right of the decimal point, so I have a yes on my first question here. Is it to the right of a non-zero digit? Well, no, there's nothing out front here except another 0. So therefore, it's not going to be significant. Non-zero digits are always significant, so the 8 counts. And then we got these 2 zeros. They're to the right of the decimal point, so we got a yes there. And they're to the right of a non-zero digit as well. So both of these zeros are going to count. So trailing zeros count towards sig figs. Here we're going to have 3 sig figs total. Another way that you might see numbers presented is with the decimal point explicitly written. If they do this, it makes a world of difference. They're then telling us that this 0 is significant. So here we have 3 sig figs. I know that can be confusing. So in example E, just to look at that again real quick, if we rewrite it and write 2,000 point, and we add that period on the end, now we have 4 sig figs. Now those zeros are going to count. Here, sandwich zeros always count, right? They're in between two non-zeros. So yes, 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 yes. And then we have these trailing zeros. And they do qualify because they're to the right of the decimal point and they're to the right of a non-zero digit. So with this crazy number here, every single value in that number is significant. 1, 2, 3, 4, 5, 6. So I'm looking at 6 sig figs for letter H. Do the next one on your own, number 5, and pause the video real quick, and then I'll post all of the answers in the next segment and explain any of the ones that I might think threw people for a loop. But take this as an opportunity to practice. So hopefully you got most of the answers right. I made a note here. These are placeholder zeros out front, and that's why we only have 1 sig fig in letter B. We have some more placeholder zeros in letter C, except they come at the end. And remember that sandwich zeros always count towards your sig figs. Scientific notation, that's a gimme. Everything counts in scientific notation. More placeholder zeros at the end, so I'm just going to count the first 3 values out front. Here's where it gets a little bit tricky, I would say. These zeros count because they're to the right of the decimal point and to the right of a non-zero digit. The same thing holds true for letter G. We have 3 sig figs because those zeros are to the right of the decimal point and to the right of the number 1, which is a non-zero digit. Sometimes students ask me, well, what if it was 1,000.000 or something like that? How close does the non-zero digit have to be? And the answer is it could be as far away as it wants to be. There's really no maximum or minimum there. So here, because these zeros are to the right of the decimal point, and because they're to the right of this number 1, even though they're far away, these zeros are significant. So we can answer yes to our questions here, and 1 counts because it's not 0. And then we have a bunch of sandwich zeros right in the middle. So I always like to throw in this extra example here. We have 7 sig figs with this value, even though the non-zero digit is pretty far away from the decimal point. All those zeros count. And then on this last one, we have 4 sig figs. So we can talk about sig figs all day, and we could do a bunch of calculations and tedious analysis of sig figs. But it's really important to remember why we need to look at sig figs so carefully. They do communicate something to the person reading the number. So when you take a measurement, the number of sig figs that you write down tells us about your measuring device. So for instance here with this ruler, let's say that this is a centimeter ruler. Looking at it real quick, how long is that pencil? The image is a little bit fuzzy. Maybe I'm looking at it and I'm like, okay, that's 8.2 centimeters. Most of us, 99.9% of us would agree that it's 8.2 centimeters. Those are the certain digits. Then we always need to estimate the last value. So if I'm really analyzing where does the tip of the pencil lie, I might think, well, it's around 8.24 centimeters. It's not quite halfway, it's a little bit less than halfway, but I don't really know. That's an estimated value, it's known as our uncertain digit. We agree to disagree when it comes to the uncertain digit. So what's the takeaway here? How do we know how to correctly read a measuring device? Well, we always want to read or measure one beyond the line. So with the centimeter ruler, the ruler was marked to the tens place, so we needed to report our number to the hundreds place. Over here, if we look at this graduated cylinder, and we're going to read at the bottom of the meniscus. So we should be looking at the bottom of this curved part. And what are these lines? This is 40, and there's 10 of them, so I'm going to figure out that it means 40, 41, 42, 43, 44, 45. Make sure you figure out, first off, what do those lines indicate? So this graduated cylinder is going up. It's marked in increments of 1 milliliter. So I need to take it one step further. I need to go one beyond that marked line, and I need to report it to the tens place. So again, looking at the bottom of the meniscus, one might say that this is 42.9 mils. And this is my uncertain or estimated digit. I love doing this in class because then oftentimes someone will say, but I think it's exactly 43 mils. I'll take it. We really don't know. We're estimating towards the end of the number on that last digit. But if someone can say it's 42.9 mils because they're going one beyond the line, you need to do the same thing. Even if it's exactly on the line, you need to say it's 43.0 mils. So if something's marked to the ones place or by ones, you need to report that value to the tens place. The thermometer that we see down here is also marked by tens, and as we move towards the left, it's kind of like a number line, right? The values get smaller and smaller. So we have -10 and -11. So again, most students will tell me we're at -11 degrees Celsius. And then if you're thinking it's exactly -11, since it's marked by ones, you better write down -11.0 degrees Celsius, one beyond the line. The marked line is to the ones, you're reporting to the tens place. But it's also okay to think, oh, it's -11.1 degrees Celsius. Somewhere around there. We agree to disagree when it comes to that last digit. For the next problem here, we have a triple beam balance. I never really see these too much except maybe at doctor's offices back in the day, I guess. How does this work? So this is a smaller one. It wouldn't be for a person, but we have 40 grams on the top and then nothing here. And then on the next one, I don't know, it's not too clear, but it looks like we have 4.6 grams, maybe something like that. But how is this marked? So 1 gram, 2 grams, 3 grams, and there's 10 spaces in between. So each line is the tens place. And so what I was thinking this is 4, 4.5, 4.6. That's the best I can see. But we have to still provide that last digit, and that lets the person know, well, we had a scale that went to the tens place, and we're going to estimate the hundreds place. So maybe it's 4.60 or 4.62. Again, it's not the best picture, so your guess is as good as mine. Just add these up, and we're going to have something like 44.62 grams. But this is the uncertain digit. So you could have 44.60, 44.65. We really don't know what that last digit is. It's kind of obscured. On this next one, number 10, this really helps illustrate the difference between the measuring devices. So if someone's using this crappy ruler, right, it doesn't have that many markings on it, they're only going to be able to estimate to the tens place. It's marked to the ones place, so they're going to go one beyond that to the tens place. So, I don't know, 5.3 centimeters, something like that. Then we get to this nicer ruler where it's marked to the tens place, so we can report our value to the hundreds place. So 5.1, 5.2, 5.3. It's not 5.3 exactly. Maybe it's 5.35 centimeters. Always go one beyond the line. And kind of a preview what the last couple of pages in this lecture packet will cover. Say we had to add up these two values. I don't know, we're taking an average. Well, you're only as good as your least precise measuring device. Let me say that one more time. You're only as good as your least precise measuring device. So when we're adding up these two values, yeah, if we put them in the calculator, we're going to get 10.65. That's what the calculator is going to spit out. But since we had this pretty poor quality ruler that only went to the tens place, we can only report our value to the tens place. So if we're to add these up, we can only say 10.7 centimeters. And I'm going to go over that in more detail, those rules for adding and subtracting values. But the reason why those rules exist when we get to them is because you're only as good as your least precise or your lowest quality measuring device. So in this last one, when you have a piece of digital equipment, all the values generated by the equipment are significant. So there's 3 sig figs that popped up on the display, or 3 digits that popped up on the display, so therefore we have 3 sig figs. The uncertain digit is built in, and you'll see some fluctuation when you use something like a scale. You'll see some fluctuation with the last value. It's still uncertain, it's built in. Take home message: when you use a piece of digital equipment, whether it be a pH meter, a scale, a spectrometer, write down all the values. They're all significant.